So, hello everyone, I'm Zhang, a PhD student from University of Illinois Urbana-Champaign, and today I'm going to present our work titled Personalized and Adaptive Virtual Reality Training for Physically Coupled Robots in Construction. So work-related musculoskeletal disorders, or also known as WMSDs, are injuries that affecting soft tissues of construction workers because of the physically demanding construction task nature, and this has been a significant problem in construction, which makes it the fifth most affected industry among others. Therefore, it highlights the needs for advanced prevention technologies to help us solve this problem. And exoskeletons have emerged as a solution for this problem, and it works by providing users with extra support or redistribute the force into other body parts to help you use more muscles to solve the to do the task. And it has been widely used in construction sites for different construction tasks. However, exoskeletons require users' body movement to align with it during the task performance, and misuse can introduce new safety risks. So effective training for exoskeleton use in construction is very important in our situation. And traditional training methods, which is often based on classroom or textbook and static for everyone. Sorry. Even though they're convenient, there are a lot of shortages, like it's theory heavy and limited users to couple with exoskeleton in real life, which means that users have less real life experience to play or to operate the exoskeleton. So this methods often ends up with lacking dynamic or user-informed instruction. Unlike static training methods, adaptive training will consider users' real-time status to adjust the training program. So when user perform an action in the training, we keep tracking their performance, and we evaluate how their performance is, and then adjust the training process accordingly, and provide real-time feedback to help them to learn it in a more effective way. And we have seen that there are a lot of applications of adaptive training in construction, like they have been used in safety training and ergonomic training, which provide us with a promising solution for this exoskeleton training in construction environment. So here's a knowledge gap that current training programs for exoskeleton use in construction are rigid and non-adaptive, which means that the methods often lack real-time responses and feedback, which will make the training program for human-robot interaction more non-effective. So our research objective is to develop a VR-based adaptive training framework that dynamically adjusts the instruction based on the real-time user performance and optimize the skill acquisition process for physically coupled exoskeleton operation in construction. To achieve this research objective, we develop an adaptive training platform for human robot coupling. So to begin with, we define key performance matrix to help us to quantify how user perform a certain construction task. And in our situation, which means the exoskeleton helped construction task, joint angle is very important because it helps us to directly indicate the user body movement and alignment with the exoskeleton during the task performance. So to calculate that joint angle, we use motion data captured by LTS and MU sensors, which are mounted on user key body parts like your waist, hips, or shoulder. And then we calculate the body segment vectors, and then the joint angles are calculated as the angles between those vectors with our cosine function. Together with those joint angles, we include the exoskeleton settings to and define those matrix as the knowledge components, and those knowledge components, or here I use KC for short. We use those KCs as inputs for the adaptive logic engine, which help us to understand how much the user have learned a specific task. So as we mentioned, we divide those tasks into different knowledge components. And for each knowledge components, we evaluate with 4 parameters, which is PL, which defines as how likely the user has mastered this skill, and PT, which means how likely the user may learn this KC, this particular KC, after training, and PG, which means the probability that the user may guess it correctly, even though they didn't know the correct performance. And for PS, it means that the user know the correct performance, but it make a sleep or wrong performance. And during the training, we keep updating those parameters to help us understand the entire process. So, for example, if a user perform a task correctly, we may think it's caused by a tooling understanding, or it may just a lucky guess. So we update PL and PG, or if it makes a wrong performance, we update PL and PS, which is the probability that he knows the correct performance, but he just make a sleep. And we combine all the PL for all the across all the cases for a specific construction task, and we calculate the task mastery probability, which is defined as PL task, and then we got a we adjust the training process based on the PL task. So if the user has mastered the task, we will increase the task difficulty and decrease the task frequency to help user focus on more unfamiliar or advanced tasks. And to evaluate the effectiveness of this platform, we did an experiment with 30 individuals. So before the training, we did a baseline task to ask them to do some common tasks in construction, like walking, bending, and squatting. And during the performing those tasks, we record their error rate, which is based on an ergonomic evaluation system called REBA. And then we did a 30 minutes VR training by either we divide the individuals into 2 groups and train either with or without adaptive training. And after training, we ask them to redo the task and compare the results. So here are the results. This figure shows this task mastery probability change for a specific participant in the adaptive training group. The upper panel shows a KC mastery probability progression. The lower one shows the mastery probability progression for different tasks. You could see that there are more incorrect performance, but with the training, the accuracy improved a lot. And here's the results for different group comparison. You could see that for both adaptive training and non-adaptive training, their error rate decreased a lot, but we could still see that adaptive training have a significant error reduction compared to non-adaptive group. So in conclusion, the adaptive training platform enhances human-robot interaction skills in physically coupled construction tasks through personalized training adjustment. And by incorporating the real-time feedback and immersive simulations for construction tasks, the platform enabled construction workers to acquire critical skills in a safe and effective manner. And for future works, we'll focus on exploring other adaptive algorithms and further our applications to other robots. And finally, I would like to extend my gratitude to my PhD advisor and my colleagues and all the funding resources. And I'm happy to answer any questions.